Picture this. You're standing in a bustling shipyard. Sparks are literally flying everywhere, massive steel plates have been meticulously joined together, and this colossal vessel is finally nearing completion. I mean, it looks like a ship, it feels like a ship, but before it can truly be called a ship, it has to prove it can withstand the ultimate relentless force of nature, water. So, in today's explainer, we're diving right into the rigorous, totally unforgiving process of hydrostatic pressure testing.
Which brings us to the million-dollar question, right? Every single weld might have passed visual inspection, the X-rays might be crystal clear, and the ultrasonic tests might show, absolute microscopic perfection inside the steel. But will it actually float? Because that's the macroscopic reality of the ocean. The ocean absolutely does not care about one perfect joint. It cares about the entire structure. A ship is only as strong as its weakest microscopic gap, and we need a bulletproof way to prove that zero gaps exist.
Okay, let's break down exactly how this works on a live test day, step by step. It's a relentless cycle, honestly. First, you fill the tank with water up to a highly specific height, what we call the test head. Then, the inspector physically walks the entire exterior of that structure, and they are looking for one thing, a weep. Just a tiny, single drop of water. If they find it, they mark it, the crew has to go in and fix it, and then the entire grueling test is run all over again. It is a process of absolute precision.
So what are we really doing here? Hydrostatic testing isn't just about getting things wet. It's about filling a tank completely with water and pressurizing it to the maximum design head. Now, the absolutely crucial word here is simultaneously. We are loading every single structural component, every plate, every seam, every flange at the exact same time. We're essentially mimicking the crushing reality of the deep sea, all while the ship is still safely sitting right there in the dry dock.
Now, if you've been following along with our previous explainers, let's bridge the gap for a second. We've talked a ton about weld inspection. Visual, magnetic particle, radiographic, all of those tests are great, and they prove that an individual joint is structurally sound. But water tightness testing, and specifically hydrostatic testing, proves that the entire massive assembly of steel actually operates as a single impenetrable sealed system. Because checking individual welds is crucial, for sure, but it simply isn't enough to guarantee the safety of a crew when they're thousands of miles from the nearest shore.
Section 1. The Physics of Pressure.
To really grasp how this works, we kind of need to look at the underlying forces at play. How do shipbuilders actually simulate the crushing weight of the ocean inside a shipyard? Well, let's unpack this classic physics equation for bottom pressure. Rho times G times H. Now don't let the math scare you. Rho is just the density of the water. G is the acceleration due to gravity, and H is the height, or the head, of the water above the point you're measuring. When you combine those three, they exert massive outward pushing forces on the tank's lowest plates. Basically, the taller the column of water inside the tank, the more intense the pressure pushing against the steel at the very bottom.
And that brings us to a very specific, absolutely crucial number, 2.4 meters. You see, classification societies mandate that the test head isn't just the normal top of the tank. Typically, you actually have to fill the water to a minimum of 2.4 meters above the tank top, or the overflow pipe, whichever gives you the greater pressure. We intentionally push the structure way past its normal operational limits, just to ensure an undeniable margin of safety.
Just think about what's actually under siege from all that water pressure. You've got your weld seams, the penetration collars where pipes pass right through the bulkheads, valve flanges, and of course the heavy structural plates themselves. The hydrostatic tests creates this inescapable truth for the steel. Water is incompressible, right? So it's going to ruthlessly seek out the absolute weakest link across all of these simultaneous loading points.
I gotta say, I absolutely love this quote because it paints such a vivid picture. Any leakage path, no matter how small, will reveal itself as a wet patch, a drip, or a weep. Just imagine the intense, slow walk of the inspector, deep inside the dark, echoing hull of a ship. They're armed with nothing but a flashlight, staring at literally thousands of feet of steel joints, just waiting for a single, telling drop of water to catch the light. It is incredibly high-stakes hide-and-seek.
Section 2. Testing the double bottom.
All right, let's focus our attention way down at the very bottom of the ship. This is the complex cellular structure designed to protect the cargo and the environment if the ship ever runs aground. We actually call this the egg box stress test. The double bottom of a ship is a really dense lattice of intersecting plates and frames. If you look at it from above, it's subdivided into these rectangular cells, literally exactly like an egg carton. And because it's segmented this way to contain flooding, each individual tank cell has to be filled and tested entirely separately to prove its own specific integrity.
So, what does this actually look like in practice? Well, the test head is set to the inner bottom plating plus that crucial 2.4 meters we just talked about. But here's the kicker. Inspectors have to walk both the outer bottom plating and the inner bottom plating, and the test has to be held for a minimum duration. Why? To give any slow winding leaks making their way through the thick steel plates the time they actually need to finally show themselves on the surface.
Section 3. Deep tanks and standpipes.
Okay, we're shifting gears and looking upward. When we talk about deep tanks and massive cargo holds, the sheer volume and depth of those spaces dramatically alter the stakes of the test. Classification Society rules actually cleanly break this down based on a tank's intended service. For your double-bottom tanks, they're tested to 2.4 meters above the inner bottom. But deep tanks and cargo tanks, those are tested to significantly greater pressure heads. Since these tanks hold massive volumes of heavy liquid cargo or ballast right up to the deck level when the ship is actually in service, the test has to simulate a far more extreme environment.
Now, this is where the engineering gets kind of wild. To achieve those extreme test heights for deep tanks, shipbuilders go to extraordinary lengths. They will actually physically alter the ship temporarily by welding these tall, vertical pipes, called standpipes, high above the main deck level. Then, they fill those pipes with water for no other reason than just to create enough artificial water pressure pushing down on the tank far below. And once the test is passed, they literally just cut the standpipes right back off. All of that immense effort really boils down to this one profound realization. Greater pressure, greater risk of leakage, greater certainty when the test is passed. By forcing the steel to hold back a towering artificial column of water in the static, controlled environment of a shipyard, the engineers are essentially buying the ultimate certainty they're going to need for the dynamic, violent reality of the open ocean.
Section 4. Proof before the launch.
As we wrap up this explainer, we arrive at the final hurdle. The ship is structurally complete, the weld inspections are totally done, but we need the final verdict before this massive vessel can ever touch the sea. Let's quickly recap. Hydrostatic testing pressurizes the entire tank simultaneously. It uses a real, physical waterhead to generate undeniable loads. It's strictly mandatory under classification rules for all tanks and watertight compartments. Ultimately, it's the absolute prerequisite for launch. Because water is the ultimate, undeniable proof of a shipbuilder's skill. You just cannot argue with a leak.
Water truly is undeniable. It's heavy, it's messy, and it finds absolutely every flaw. But I want to leave you with a provocative thought here. What happens if you have a critical, watertight compartment on a ship, but it's full of highly delicate electronic equipment? Or maybe it's just too vast and you literally cannot flood it with water. How do you prove it's watertight without a single drop? Well, it involves low air pressure and just a little bit of soapy water. And that is exactly what we're going to uncover in our next explainer. See you then.